The next reaction of carbohydrates is kind of an interesting one. It's called the osazone formation. So this is where we take a carbohydrate and we react it with three equivalents of phenylhydrazine. So again, I'm going to use D-glucose as my example. And I'm going to react D-glucose with phenylhydrazine. So if you recall from when we were learning about aldehyde chemistry, right, and the addition reactions of aldehydes, we learned about the formation of acetals. We also learned, though, about the formation of imines and enamines. So if you react an aldehyde with a primary amine, you get an imine. So here is what we are doing. We're taking the open chain aldehyde of D-glucose and reacting it with phenylenediamine. So phenylenediamine, the nitrogen at the end, so the nitrogen on the right-hand side, is going to form an imine. But notice the question is, why do I have three equivalents of phenylenediamine? Well, the reason for that is because when I isolate the product, this is actually what I get. And so notice there are two carbon-nitrogen imine bonds. I don't get a simple imine formation at the aldehyde carbon. I actually get an imine formation at both C1 and C2. And this is called an osazone. Now, in order to elucidate what's going on there, I also have to think about what my side products are in this reaction. So notice I say I need three equivalents of phenylhydrazine. I think I said phenylenediamine. I meant phenylhydrazine. So this is phenylhydrazine. And the byproducts of this reaction, I get one equivalent of aniline. So benzene ring with an NH2 group, right, is aniline. I also get an equivalent of ammonia, and then I get the loss of water. So how do I explain why I need three equivalents of phenylhydrazine and two of them add to the ring, and then I produce aniline and ammonia as a byproduct of this particular reaction? Well, in order to do that, we have to think about, again, the mechanism of this reaction. And it's a relatively lengthy reaction, and to use glucose as my example, I'd be taking up a lot of space. So instead, we'll go back to a little shorter tetrose like this, right, D-erythrose, and we can still follow along and figure out what's going on here. So obviously the first step of a carbohydrate, in this case D-erythrose, reacting with phenylhydrazine is I'm going to form the imine. So the aldehyde is going to be converted into an imine, right? So this is what that looks like. So the carbon nitrogen double bond is forming, and then of course that nitrogen has an NH with a benzene ring, right? You can almost think of it as an aniline substituent coming off of the nitrogen. And of course, C2, C3, and C4 haven't changed at all. So here's C2, C3, C4. And this is what we call an imine. More specifically, when phenylhydrazine reacts with an aldehyde, we get a derivative called a phenylhydrazone. Right? That's what it's called, a phenylhydrazone. And this is what we would have expected really to get when reacting any sugar in its free aldose form with phenylhydrazine. We would expect to get an imine, but obviously we don't get an imine. So what's going on here? Well, if we think about the structure of this imine, and we kind of compare it to the structure of the aldehyde. So notice instead of a carbon-oxygen double bond on the left, I have a carbon-nitrogen double bond. And that's really the big difference. So what do we know about the chemistry of aldehydes? We know aldehydes have acidic hydrogens, and in basic conditions, and phenylhydrazine is certainly a base, we can actually get deprotonation of the carbon and then reprotonation, and we form enols. Well, guess what? We can form enamines, right? So this is called an enamine, but notice there's also an enol there. So there's a carbon-carbon double bond, and the nitrogen, right, has been protonated. So instead of the OH, I have an NH protonation. This is an enamine, but at the same time, notice I also have an enol. So C2, the OH of C2 with the double bond of C1 gives me an enol. So I have both an enamine and an enol in equilibrium with the imine. Okay, now we know that enols are also in equilibrium with their ketones. And so I can form a ketone in equilibrium with the enol. So that's important to understand. We went from the enamine, noticing we also form an enol in the process, and the enol is in equilibrium with the ketone. So it's all about keto-enol tautomerism. Now, if a ketone can form on C2, I can react it with another equivalent of phenylhydrazine. And so that phenylhydrazine can add to that carbon-oxygen double bond and give me another amine. So now I have at the top an amine and on C2 an imine. So I form a new imine bond. So I have now at C1 an amine bond and at C2 an imine bond, right? All right, so I'm going to take this structure, and obviously we're not quite done because notice I told you we actually need 3 equivalents of phenylhydrazine, and aniline's coming off and ammonia's coming off, and this isn't this is not what we call our osazone, right? The osazone has essentially 2 imines. So in this particular structure, I have 1 imine and 1 enamine. So something else has to be happening. Well, what I'm going to do is I'm going to redraw this new imine on the next page here. So I'm simply redrawing that structure that was on that last page. And I'm going to think about what can happen with this imine. Well, again, notice imines and enamines are in equilibrium. They can tautomerize. And so I can get the enamine from the imine of it. And of course, I still have the amine that's coming off of that C1. Now, when I form the enamine, something interesting happens. What happens is that nitrogen-nitrogen bond, which is relatively a relatively weak bond, can actually dissociate and protonate. So the proton is going to go onto the nitrogen on the right. Notice that what is that going to give me? That's going to give me NH2 with the benzene. That is my aniline, right? Now when I remove that proton, the electrons from that nitrogen-hydrogen bond are going to reform the imine bond, and the carbon-carbon, the alkene bond, that pi bond, is then going to resonate back into form another imine carbon-nitrogen bond, right? Because I'm actually losing electrons on that nitrogen that's coming off of C1. So now I can redraw that rearrangement, and what do I get? I get a double bond on C1, I get a double bond to nitrogen, which has a hydrogen off of it. On C2, I now have another double bond of nitrogen, which has the aniline coming off of it. I also have liberated aniline as one of my products, so there is that formation of aniline. So now I have what we call a diimine, and diimines are with that carbon nitrogen uh, NH imine is actually relatively unstable. And if I have another equivalent of phenylhydrazine around, essentially I can basically substitute the phenylhydrazine imine for the NH imine. And this is where I actually start to form my osazone, right? So this is the osazone, and notice ammonia from that NH actually comes off. So in a series of equilibrium processes, which you should be able to work out, but you don't really need to know that. I'll never test you on that. You get the osazone, right? So this is kind of a unique feature of carbohydrates, is that they form osazone complexes. All right, now something a little bit easier to kind of digest is what is another type of reaction called ether and ester formations, right? So obviously we have, we're working with alcohols. Carbohydrates are alcohols, and alcohols can form ethers, and of course they can also form esters, which we've seen time and time again. So we know that, with all of these alcohols, we could substitute in basic conditions, treating this with methyl iodide. This is like a Williamson ether synthesis, right? We use silver oxide as our base, and the silver oxide will remove pretty much any of the protons on any of the OH groups. And if I have an excess amount of methyl iodide around, I can essentially get methyl ethers of all of the alcohols. And so the structure of that product, right, the OH on the anomeric carbon gets converted into a methyl ether. I get another methyl ether on C2 and on C3 and on C4. Of course, not on C5, but on C6, I can also get a methyl. And so this is what we refer to as pentamethyl ether derivatives of carbohydrates, right? In particular of glucose, because we're talking about glucose here. Now, interestingly enough, I can selectively form an ether at the anomeric carbon. So again, if I take a look at glucose in its chair conformation, and I treat it with methanol in catalytic acidic amounts. So what happens is, again, in acidic conditions, the OH groups could be protonated potentially, right? And you get a substitution reaction with methanol. When we look at the product of this reaction, this is what we observe. We observe that the anomeric OH gets converted into a methyl group, but the other alcohols stay the same. And so methylation only is occurring at the anomeric carbon. When this happens, and when you get substitution at the anomeric carbon and to form an ether, these are called glycosides. And glycosides are actually very important in terms of biochemical pathways. So, for example, nucleic acids are glycosides, and so we talk about glycosidic bonds a lot when you get into biochemistry. That will become important for you to recognize, right? So the question is, well, why? Why is it that in acidic conditions, and this is the key, acidic conditions, we only get methylation at the anomeric carbon? Well, the reason why is the same reason as most of the other times, right? So when we protonate any of those OH groups, notice only one of the OH groups can be stabilized by That's right, resonance, resonance. So notice if I protonate that anomeric carbon, I have the hemiacetal, and that oxygen in the ring of my hemiacetal can donate electron density and kick off, help facilitate the loss of that water. And so I generate this particular intermediate. And if methanol is around, now methanol can attack that anomeric carbon, and the electrons can go back up onto the oxygen in the ring. And then you have essentially methylated that anomeric carbon. All of the other OH groups could form secondary carbocations, except for C6, that would be a primary carbocation, and that's certainly not favored. So if we if we use a catalytic amount of HCl in methanol, we can selectively methylate the anomeric carbon. Now, we can actually take advantage of this what I call C1 acetal hemiacetal reactivity, because notice the reason why that that OH group on the anomeric carbon can come off is because it is a hemiacetal. And so we talked about, in the past we've talked about the reactivity of aldehydes and forming hemiacetals, and then they go on to form acetals. Basically, you're going from a hemiacetal to an acetal in that process. Now, how do we take advantage of it? Well, notice, what if I methylated all of them? And I, of course, know how to do that, right? In basic conditions, reacting the carbohydrate with silver oxide and methyl iodide, I can methylate all of them, right? Now, notice, if I take that pentamethyl product and I react it with water in a catalytic amount of HCl, again, the same process is going to happen. I'm going to protonate the anomeric OCH3 acetal. The oxygen on the ring can come in, kick that off, and then water can go back on. And so basically, I can now get the OH solely on the anomeric carbon. Now, why would I want to do something like this? Because notice all of the other carbons, C2, 3, 4, and 6, all remain as methyl ethers. Well, I can use this chemistry along with other types of reactions. One in particular is oxidation with periodic acid to determine whether a sugar like glucose actually exists as a pyranose ring or a furanose ring, right? How would I do something like that? Well, let's say I have now the glycoside of glucose, right? So here I have glucose, but it has the anomeric carbon has been methylated, and I treat this with periodic acid. Now recall, what does periodic acid do? It cleaves vicinal diols, right? It cleaves vicinal diols. And notice I have some vicinal diols here. I have a vicinal diol here, where I'm going to get cleavage, and I have a vicinal diol here, where I get another cleavage. Notice the strategy of methylating the anomeric carbon, because if that was an OH group, I'd have another cleavage going on, and then I'd get I'd basically get the same product in of a furanose ring as I would in the pyranose ring, right? But now, since I've strategically methylated that, what are my products? Well, so I'll start at C4. C4, that OH gets converted into an aldehyde, and then of course I have C5, which has the oxygen, which is connected to C1, which has that OCH3. So hopefully you can kind of see, I've tried to draw the connectivity. And then of course C6 is coming off of C5, C2 is coming off of C1, and that C2 becomes an aldehyde, and now C6 is simply an OH because there isn't a diol there. So C6 stays as an OH, and then C2 becomes an aldehyde. Now, what happens to C3? Well, C3 is unique in that there's actually, it's in between, it isn't a vicinal diol, it's a vicinal triol. And whenever you have a triol, and so there's a carbon with an OH coming off of it, it doesn't form formaldehyde like a terminal diol would. It forms formic acid. So this is what we would expect to see if glucose exists as the pyranose ring. But what if glucose existed as mainly the furanose ring? Well, again, I can do the same thing, and I can methylate that anomeric carbon, and I can look at the product of reacting this with periodic acid. And so I see when I evaluate this particular structure, again, there are two diols. I would get cleavage at both of these locations, but notice the products are going to be very different, right? So one of the products is this, right? So where I have, if I'm talking about C4, so C5 becomes an aldehyde, and C3 becomes an aldehyde, and C1 stays the same, and C2 becomes an aldehyde. And now the only one that I have left to account for is C6. And of course, notice it is a terminal diol, and so it's going to give me formaldehyde. So notice with the pyranose ring, I would expect to get formic acid, and then the structure above. And then with the furanose ring, I would expect to get formaldehyde. Well, this is actually what I observe. And so based on that, I can determine, oh, okay, it must exist mainly as the pyranose ring. So I talked about ether formation, and you can see what we can do with ether formations. We can also esterify carbohydrates, right? If I have an alcohol, I can react that alcohol with an acid chloride or an acid anhydride, and I get esters. So if I take glucose here and I treat glucose with acetyl chloride or acid anhydride in excess amount, basically what happens, I can esterify all of those OH groups, and so that's exactly what I get here, right? So I'm forming acetic, esters of acetate all around. And so this is simply a glimpse of what we can do with carbohydrates. If you think a little bit, we can protect them with ketones, right? Where you have some types of steric strain with vicinal diols. Vicinal diols aren't readily used to protect ketones, but other diols can. So you can actually protect the C4OH and C6OH if you react it with a ketone and stuff like that. So, and we're not going to get into that, but I just want to give you a glimpse of what you can actually do with carbohydrates.